Hello, sir. Good afternoon. Sir, is my voice audible?
Yes, sir. Hello, good afternoon. Can you hear me, sir?
Yeah, yes, sir. It is audible, sir. Define this side, sir. Sir, currently the quiz is going on.
Okay.
And the quiz is scheduled till 2 p.m. and the participants are expected to join by next 1 or 2 minutes, sir.
Okay, no problem.
Sir, if you permit, then we can start the sessions. Sir, is my voice audible?
Yes, I'm sharing my screen. I sent you one message, so please you could also check your message. Okay, so good afternoon. Let's continue the lecture for today. So today we are going to talk about the continuation of a sliding mode control. So basically, as you remember that yesterday, day before yesterday, so we talked about the introduction to a sliding mode control, and we also looked at some fundamental aspect of this control technology. So today we'll continue again. So about the slide remote control design, and then I will show you some different kind of result has been developed based on this strategy. Of course, a slide remote control, the variable structural system VSS, so it has a long history in control. So therefore, many extension, many development, many application you can expect for this strategy. So based on the two fundamental aspects of the sliding mode control, it become of interest. The first, it was the finite time convergence. It means that the state trajectories can approach to some surface and can be regulated in the finite time. The second property for the sliding mode control is the robustness. And that's it based on these two aspects. So we can continue to look at the more basic features of the sliding mode control in the lecture today. So today I have prepared some lectures based on a schedule. First is the configuration of a sliding mode control. I will talk about the fault, about the tolerant control, about diagnosis, and also I will also give some lectures about the cyber security and particular applications to autonomous cars. So that's it for today. So basically we can cover this important aspect in our lectures. Okay, so let's continue. So about the sliding mode control, as you remember that one of the important things, so you need to basically to find this sliding manifold, sigma x. Okay, so the sigma x could be the nonlinear function. So you should think about some sort of a linear form. So either you can choose linear or nonlinear shape. But anyway, so this is a sort of a manifold. It means that they can attract to all the trajectories, so to one particular surface. So this manifold sigma x, so in the linear form, for instance, you can define it like this, as Cx, so equals 0. So here you can see that the parametric C, so the metric C is basically your design. So design parameter. So you need to choose the metric C. But of course, it's not limited to this shape. So as I said that the sigma x also could be nonlinear, but depends to your case. So it depends how do you want to look at the control design, and that's it. You can look at the different manifold, so in your case. So there is one issue we need to clarify. So the issue is that how is the sliding manifold design when one of the previously described canonical form is selected? So if you remember that we talked about the four type of the canonical form in our lecture before. So now the point is that if you have one of these particular canonical form, so how this sliding the manifold can be designed? So this is one question. So basically, and this means that, so this question means that we are talking about some classical control design. So in such a way that you have a canonical form in the system model, in the dynamics, and also you try to design the sliding manifold, so that based on this strategy. So in this case, we can see that in the case of the design of the sigma x for the canonical forms, so let's start with the reduced form. So you remember that the first techniques we talked in the canonical form, so in the shape of the reduced form. So we know that if you look at the state vector, so it can be split to x1, x2. So it means that your vector x, so you can represent it like x1, x2, okay? So you can split it into two parts. So when you split it into x1, x2, and then you can design sigma x like this. So sigma x is composed of x1, x2, like this. And then you remember that the sigma x, it should be c multiply x, okay? This was the linear shape. So now the x is the x1, x2. So now this is the x1, x2. And also the metric C also can be partitioned to C1, C2. And therefore, so this could be the representation. Okay, but if you're doing like this, because you want to reach the reduced form is a function of x1, okay? So you remember that the reduced form should be in the function of x1. And therefore, x2 should be get rid of x2 in your formulation. And that's it. From this mathematics, you can say that the c1 x1, so plus a c2 x2, so this should be equal zeros. And then if you want to get explicitly the reduced form in the shape of x1, So what does it mean? It means that the x2 so should be removed. How to remove x2? So x2 from here should be minus the c2 inverse of the c1 x1. Okay. So now from here you can see that if you want to get x2, the x2 should exist. Okay. So it means that you should calculate it. And if x2 should exist, it means that the matrix C2, so the matrix C2 should be basically the full rank, okay? So it means that you should be able to make an inverse. Okay, so now the matrix C2 is a non-singular, and that's it. You can calculate x2, and then when you have x2, it means that the x2 becomes this. And then if you put x2 in your mathematical formulation, so then you can see that the x.1 is this, and then x is the x1, x2, right? And then instead of x2, you can put this. Okay, so this representation, so in a sliding mode, so the system has such a behavior. There is an algebraic relation. So this formulation, it says that there is some sort of the algebraic relation between the x1, x2, and here you have basically the dynamics. So here you have a dynamics. Okay, so this is the philosophy for a reduced form, and now you see that the task is very simple. Just you need to find C1, C2, and therefore the question is how to find these matrices. So in the reduced form, so if the A1 is linear, so if A1 is linear, so here, so that is a function of AX and T. So if your function AXT is a linear, for instance, like this A11 x1 plus A12 x2. So in the case of the linear, basically the function A, so then the reduced dynamics become this. So now you will get these dynamics. So for the overall system on the sliding manifold. So the interesting point is that here you have a new matrix. So this matrix, and this matrix. So if you choose the matrix F, so basically is equal minus C2 inverse C1, okay? So based on this selection F, you have this mathematical formulation. So now the whole stability goes to the eigenvalues of this matrix. And therefore you can choose F. So basically if the A1 and A12 is controlable, okay? So in this case, you are able to choose it. But you know about controllability. So here it says that A11, A12 is controllable, but the controllability, so this condition has some sort of some constraint on the selection of A11, A12. But if A11, A12 is not controllable, so I can tell you that if, so A11, so A12 is not, so it's not fully controllable. It's not fully controllable. So what should we do? But if it's not fully controllable, so you need to check a stabilizability, okay? So you need to check a stabilizability. So in control, we have two concepts. One concept is the controllability. The second concept is a stabilizability. These are totally different. So these are not equivalent, right? So the controllability means, so this matrix A11, A12 should follow some rank of some formulation. So you know from the control course. So if there's such a controllability matrix, the rank is complete. The system is fully controllable. But in such a way that this is not controllable, you need to check a stabilizability. So I can give you one example. What does it mean? What does it mean, a stabilizability? So assume that you have a function GS, okay? Let's assume that you have a function GS, okay? So GS is equal to 1 over, for example, S plus 1 multiplied S plus 2. Okay, so if you have such a transfer function, so this, if you find the matrix A and matrix B, if you find the matrix A and B, so for this matrix, so you can see that this system is a fully controllable. So it means that this system is controllable, okay? So you can find it as a controllable. But if I give you another function, for example, if I give you GS, for example, and then you can basically choose the matrix F. So there is a lot of formulation like the Ackermann. So you can use, for example, the Ackermann approach to choose matrix F. Okay, so now when you have the because the F is this, and when you choose F, now you have a two parameters, C1, C2, then it's up to you how to choose C1, C2. So therefore, based on C1, C2, then you will get the Cx. So sigma x is the design. So it means that you finally, so you can design it, you can construct it. Okay, so this is the main idea. So the main philosophy basically for choosing the sigma x for the radius form in the canonical form. Okay, so another form, it was the contractility. So you remember that the second canonical form is the contractility form. So what does it mean? If you remember that in the contractility form, the system can be split into the M subsystems. It means that you can split the system to the several subsystems, for example, M subsystem. And then the sigma I, so for each subsystem from 1 to n, it can be designed from this formulation, sigma I transpose xi. But you need to remember that here the vector x, so it can be composed to integral x1 up to, for example, xn. So this is a several subsystems. And then each x1, it has a dimension n1, for example, and xn, it has a, for example, dimension, for example, another dimension like nn. So now the whole dimension should be equal to dimension n for the vector x. Okay, so now the point is that the major requirement how to choose CI, because here you need to choose CI for each subsystem, so you need to choose CI such that the overall the overall control system in a sliding mode asymptotically stable. So it means that each subsystem should be stabilized and then depend on the choice of CI. So the dynamics of each subsystem in a sliding mode can be assigned by selecting the component of CI. Okay, so the question is how to choose the parameter of CI. So now each equivalent subsystem has the order Ni-1. It means that this is the order for each subsystem. So it has such an order, and it has a canonical contributive form. And then you can find the corresponding characteristic polynomial has the component of CI as the coefficient. Okay, so this is just the partitioning. So you need to partition X to the several subsystems, like the M subsystem. And then you need to choose for each subsystem sigma I, you need to find CI. So not the question is that how to find CI, but you need to choose CI in such a way that each subsystem should be asymptotically stable. Okay, so another form we discussed also in our previous lecture, it was about the decoupled input-output form. So you remember that when we talked about the decoupling input-output form, so you need to look at the degree of the system, and therefore, so it's very similar to the case of the contributive form. So that's it. The approach for this case is also very similar to the contributive form. So because if you remember that if you back to our decomposition, because we talked about a contributive form here. So this was about the decoupled input-output form. You remember that we discussed about it in the last lecture. So you need to look at the relative R, and it means that for each subsystem, you have a different relativity R1 to Rn. And then if the R is equal n as the order of the system, then you can find this shape. And for this system, you need to find the decoupled input-output form. So in this shape, you need to take as Ri derivative from the Yi such that the Ui can be appeared. So in this case, this is your decoupled form, and this decoupled form, so if you find it, is very similar to the contributive form, and then you can basically to apply the same idea for this case. Okay, so now you can see that the decoupled input-output form is also very similar to the contributive form. So another shape, it was about for the canonical form, it was a normal form. Okay, so the normal form, so basically, this also can be called as a zero dynamics. So what does it mean, the zero dynamic? The zero dynamic, it says that there is some internal dynamics, so they can bring the zero to the output. It means that it can be obtained by posing equal to zero the output. So how to bring the output, for example, equal zeros? So in this case, and also, of course, then also the derivatives. So in this case, you can see that the output is zeros. And in this case, you need to find some zero dynamics, like the eta. The eta here is the zero dynamics. So in this case, if you want to design the sigma x for the canonical form in the shape of the normal form, so you need to choose the basic the zero dynamics should be asymptotically stable. So how to make it a typical choice for a sliding variable component for the sigma x. So you can choose a sigma x, for example, equals zeros. You can choose sigma I like this. Sigma I is the CI transpose Zi, but you need to remember that for this case, sigma I, so sigma is chosen as in the contributive form. So the basic is that if you understand the contributive form, so easily you can handle a decoupled form, you can handle normal form, because the selection of the CI is very similar to the concept before. So to assign the dynamic to the for the reduced order form. Okay, so now you can see that this is another basically the canonical form, and it's very important because you remember, you know that zero dynamic is very important in control. Why? Because the zero dynamic is an internal dynamics, and it brings the output to zeros. And if you don't control it, then the system becomes in a very critical situation. Therefore, stabilization of the zero dynamics is the first to how to stabilize the zero dynamics. You can do it by choosing the sigma R in such a way. Okay, so now the existence of the sliding mode. After the design of the sliding manifold is necessary basically to guarantee the existence. So the existence of the sliding mode, so we need to look at it, how to guarantee that the sliding mode exists. So a sliding mode exists if in a vicinity of the sliding manifold sigma x zeros, the vector tangent to the state trajectory of the control system is always directed toward the sliding manifold. So it means that if the state are hitting the manifold, so the tangent is always should be in the direction to the sliding manifold, and this means that the sliding mode exists. Okay, so in this case, around of the sliding manifold sigma x, so the vector tangent with the state trajectories, so always directed towards the sliding manifold. It means that the state should remains more or less after the some time, or the remains or stabilize on the manifold. So if this condition is satisfied, then we can guarantee that a state can be stabilized, can remain on basically on this case. Okay, so now the existence of the sliding basically the mode. So the ideal and practical sliding mode. So what are the ideal and the practical sliding mode? So the ideal sliding mode is enforced if the state trajectory of the control system is such that the sigma x zero. It means that if the reaching time, because we talked about this before. For example, if this is your sigma x, so if from the initial condition x zeros, if the state it arrives to this at the time tr, this is the time tr, okay, reaches at the time tr. Okay, so after the tr, for each t bigger than tr, so a state should basically remains on the sigma x. So this part is the reaching time. The reaching time is this, and this time is the motion time, or we call it the sliding motion. So a sliding motion. Okay. So this sliding motion or the chattering. So this should be controlled. Okay. So this is basically the ideal. Of course, we would like to keep it as far as possible in all zeros. But to have an ideal sliding mode, the control variable has to switch at the infinite frequency. So this is not possible, okay? So basically, the ideal case, so maybe not possible, and therefore, we should say that if not possible, so we should say that the sigma x, so this should be approximately zeros. So this approximation means, so this motion, right? This kind of the motion, and in a sliding mode we call it as a chattering. Okay. So now the topic of the chattering so it becomes on the table. So now in this slide there are two information. One information is the reaching time, is the TR. Another is about the chattering. The chattering is for the each time. So there is a bigger than basically TR, okay? So now what is the task? The task is that first you need to bring a state to the surface. This is phase one, okay? The first step is this. So, and then you need to design the control. You need to design the control in such a way that it remains arrived to the surface in a short time. And then the chattering also should be controlled. So a state evolution in the vicinity of the sliding manifold is called the practical sliding mode. So then now you can see that the PSN, so the practical sliding mode, so it also represents the chattering. So you need to remember that how you can how you are able to reduce this oscillation, how to reduce this oscillation. So I can tell you that usually when you design the control signal in a sliding mode, so for example, you have some coefficient, for example, some coefficient to multiply the sign, okay? For example, sign of x. So this sign of x is gives some switching, and therefore this switching. So we talk about this switch. So this switch, it means that you have some sort of a function, okay? So therefore, if you want to make it a PSM as a practical sliding mode, so the sign function, so this can be approximated. So this can be approximated, for example, with another function, for example, x over the for example norm of x plus epsilon. Okay, so this is a very interesting trick. So this we call it a trick. Okay, so the trick is like this. So when you design the sliding mode control, so I told you that the system should have some switching in the control signal. But this switching, it needs a lot of energy because you cannot do the infinite frequency. So therefore, usually in a sliding mode control, if you want to get more smooth and if you want to control the chattering, or if you want to come to PSM, the practical sliding mode, so the sine x, because you know that the sine x is x over the norm of x, right? Because we know that the x over norm of x is a sine. But you need to add something here, and therefore you can change it like this. So this epsilon is too small, okay? So by adding very, very, very small values of epsilon, so you can avoid so this kind of this infinite switching, and you can also get a quicker or a smooth response. And this is basically we need to do it in our sliding mode control design. So sometimes when you write a paper, when you get the control signal like this, so the first question you will get from the reviewers ask you that how is possible to apply this control, because you should have some sort of the switching in your control. So the answer is that you can modify the control signal like this, and then you can basically get the much smooth response. Okay, so this is basically what I'm talking about, the ideal and practical. So this is basically the ideal case. Ideal, it means that you are reaching time at the time TR, okay? And then for each time bigger than TR, so you should have exactly zeros, okay? But this is not possible, because this is not possible to make it. And therefore, you need to accept some oscillation like this, okay? So this is a chattering, and therefore, if you want to reduce the chattering, so you can modify here, you can modify control. So you can modify control signal, for example, the sine function. So sine of x, you can change it to x over x plus epsilon. Okay. So now you can see that you can control, because this chattering, so this chattering also should be controlled in such a way that so the range should not be too high, and that's it. This is the art of the control signal. It means that your control signal UT, so is a big challenge for the PSM, for the practical a practical sliding mode. Okay, so the existence problem. So the existence problem is a stability problem. So the first thing that you need to satisfy is stability. So stability should be guaranteed. So a existence of a sliding mode requires that state trajectories at least from the neighborhood of the S. Stay at the time zeros. So you want to do such a basic stabilization. And that's it. If you want to satisfy the reachability for all the global state, so it means that if your attraction domain can coincide with the whole state, then you have a global reachability. So existence of a sliding mode can be proved by using the Lyapunov function. So that's it. For stability, we always use the Lyapunov base, and therefore you need to choose what is your Vx. So the Lyapunov function Vx, so this should be designed, and how to design it. So this is the task. Okay, so the first step is existence for a static problem. It means that you need to choose the function Vx. Okay, so now there is a lot of research. So many researchers, they develop many Lyapunov functions. And if you choose the new Lyapunov function, then you can design a new control. And therefore, the main task for the researcher in this area is to pay attention how to develop a less conservative Lyapunov function. So it means that if you choose the less conservative design, so it means that you can reach to more global, so for example, the reachability. So basically, this means that we need to pay attention to Vx, and this is a very important task. So the one simple Vx. So one of the simple Vx, why not choose against sigma x? Because you remember that the sigma x is a one variable, right, as a sliding manifold. So why not choose Vx based on sigma x in the quadratic form? Okay, the half of the sigma x cube. So this function, so basically is a positive. And also, you can also check it out, and then you can check out what is the v dot x, okay? So this should be calculated. So you need to remember that the sigma dot depends on the control variables. Then it's a discontinuous on the sigma zeros. So you remember that the sigma x, it depends on the control variable, and control variable u, so it has some switching. This has some switching, and therefore at the sigma zeros, therefore at the sigma zeros, there is some discontinuity. Okay, we need to remember in mind. So you need to remember that this point. But if you want to take the derivative, the control variable has to be chosen and such that the attraction rate of v dot x. So this relation should be satisfied. So okay. So one question for you: how to calculate it? How to calculate v dot x? Okay. So the question is how to calculate v dot x. So v dot x is a dv over dx, right? You know from for example, dv over dt, okay? It's a dv over dt is a v dot x. But the dv over dt, because your function vx depends to sigma x. And then you can say that the dV over dt is equal to dV respect to the d sigma and multiply, so d sigma over dt. So this is a basically we have a chain rule that you can use the chain rule in mathematics. So by using the chain rule, so you can write dV over dt is equal to dV respect to d sigma multiplied d sigma over dt. Okay, so dV respect to d sigma, so Vx is at this. And then you can see that the dV or the round of V, for example, round of V respect to the sigma, so it's equal half multiplied 2 multiply sigma x, okay? And therefore, this becomes sigma x. So here, then you can write here that the round of V respect to round of sigma, this becomes sigma x, multiply round of sigma over dt or d sigma over dt, this becomes sigma dot, okay? So that's it. When you have this formulation, so we need to remember that how to calculate, because this derivative, you need to know that how to make it. Okay, so v dot x becomes sigma sigma dot, and then the vx is positive, so v dot x should be negative, okay? And then this relation should be satisfied. Okay, so for by choosing the control signal, so this condition should be satisfied. So for the reachability condition, so v dot x basically should be the negative. And what does it mean? It means that your state trajectories, it means that your state trajectories for this sigma x, so this state from the x at the time zeros, they can reach to this at this time. So this was basically the reachability condition. Okay. So if you want to keep it to satisfy this condition of the time tr, so you can satisfy this condition. So if you satisfy this condition, it means that your state trajectories can move basically to the surface. Okay. But of course, after this, there could be some sort of a chatter. So now we come to prove the finite time. So if you want to look at the FT, because FT is one of the important aspects of the SMC for a sliding mode control. So we need to look at the finite time convergence is very important. Okay, so one alternative way to express the reachability condition is the following. So for the sake of simplicity, the single input case is considered. Now we have only the single input for the single input. So sigma dot, so it should be negative, right? So then we can change it to this. So we can say that the sigma dot should be less than minus the gamma, the norm of sigma, and this is and also for the reachability conditions. So the gamma should be positive if we choose the gamma positive, and if this condition is satisfied, of course, this means that this is also negative, and this is also true. So if you want to satisfy this condition, so it means that the v dot x, because this is a v dot x, okay, this is a v dot. So the v dot x should be less than minus gamma prime of the norm root square of the vx. So because you know that the vx, it wasn't like this, it was the half of the sigma x, okay, square. And from here you know that the sigma x, it becomes I hope everything is, you can hear me. So sorry, I don't know why My mic, it was unmuted. It was muted. Okay, so now we know, again, I can repeat it again. So the finite time convergence, so basically is a property for the SMC. So for the reachability condition for the single input, so basically we can do like this. Instead of saying that the v dot x, so it should be the sigma that should be negative, you could substitute by this term minus a gamma norm of the sigma, because this is also negative. So from here you can see that the v dot x is less than this term, because the vx, so the sigma x, the norm of sigma, you can substitute it from this formulation, so here, and then you have this mathematical formulation. So this mathematical formulation, so if you look at the differential equation and the solution for this, so it's possible to find, so the upper bound for the reaching time, the TR, by integrating the gamma reachability conditions, so between the time zeros to the TR. So now if you look at the solution, because here usually there is some lemma, so there is some lemma, but it can be proved. So there is some lemma says that if this condition satisfied, then you can reach to this condition. The sigma at the TR minus the sigma at the time zeros. So it also the less than these conditions. And it means that from here, so you are able to find the TR, the reaching time less than this. So reaching time less than the norm of sigma zeros less than the gamma, this is FT. It means that you can guarantee the convergence in a finite time, and the TR is a bounded. You see, is less than infinity, and that's it. Is a finite time convergence. So this property is very important. And of course, if you play with the gamma, because it depends to your gamma. If you change the gamma, you can also change the TR. So if you want to, for example, if you want to decrease the TR, then the gamma should increase. Okay, the gamma should increase. But you need to pay attention that if the gamma increase, then you need to see what is the control, because the control signal should be not saturated, because another problem is about the saturation. So now you see that this trade-off. So this trade-off between the fast response and also the saturation, because you need to pay attention. So how to find how to choose this gamma, because by changing the gamma, basically you can change the speed of the convergence. Okay, so here there are some interesting textbooks for you. So if you are interested, you can also look at some fundamental aspect of the sliding remote control. So there is a lot of interesting works. So from the Professor Hetkin, so from Professor Ferrara. So there is a lot of interesting textbooks, so you can find it for your interest. Okay, any question up to now? Or? Okay, so if there is no question, so then I can also show you some other results about the slide remote control. Okay, so uh, I want to show you some new results. So basically, Okay, so now I want to show you a little bit how this kind of basically a sliding mode control so can be added to the network control and also with some complexity from CPS. So the topic I want to, yes, do you have any question? Yes. Okay, please, I think you have a question. You can ask me the question. Okay, Desi, do you have any question or you raise your hand? Okay.
Sir, what is, excuse me?
Yes, yes, please. Okay.
Hello?
Okay, what's your question is?
Sir, finite time, fixed time, stability.
Okay, so about the final time. Okay, we noticed that, okay, so I can explain you here that, for SMC, so a sliding mode control, so it says that I have a property of the FT, the final time. The final time convergence, so we notice that it depends basically to the reaching time. It means that the TR is less than, for example, sigma zeros over for example, the gamma. So it means that this is a less than infinity, and therefore this is a basic, we call it the final time. So the final time means that it reached in a short time, but this is a final time, not in the infinite time. But of course, we notice that if you want to get a fast response, if the TR decrease, so now you can see that the gamma should increase. But if you increase the gamma, then you can decrease the TR. And if you decrease TR, it means that the final time convergence, it becomes faster. But of course, there is some problem. The problem is that there is a trade-off between this case. You need to look at the control signal, okay? Because the control signal, so it should not saturate, because if you increase the gamma, so maybe the control signal will be saturated, and therefore you need to pay attention. You cannot increase it too much. There is a one a gamma max, okay? For example, for the gamma max, in order the system not saturating, and for the gamma max, and then you can find the TR as a basic the TR mean. It means that how much you can make it system fast. So this concept is a finite time. But in control, we have another concept about the fixed time, okay? So the fixed time, so fixed time is also a very important topic. So the fixed time, it means that so your TR should be exactly at the given time, for example, the T as a T given, okay? So it means that based on what the parameter T, so you like it, you have it, then you can design the control. Okay, so if your TR in the fixed time, if your parameter T for the reaching time, based on this formulation, so you can you see that the fixed time is more difficult than the finite time, because the finite time you can be between the one up to the TR mean, but here the T is given. But of course, you can follow some extension, some modification of a sliding mode, so such that you could be also able so to satisfy the fixed time. So, but in fact, I told you also in the last lecture. So these two topics are different. So, but the difference is that you need to pay attention that if the fixed time is doable or not, because sometimes you cannot make it by the regular sliding mode, because a sliding mode you have some constraint in terms of the selection of the final time based on the gamma and based on saturation. So now usually if we look at the research, so some research is also looking at the fixed time and also finite time. But that's it. You need to distinguish. You need to distinguish between these two parts. But today I just talked about the finite time, but the fixed time is also should be the modification. You can modify your sliding mode control also to be able to satisfy the fixed time. So, but I didn't discuss it today. But if you are interested, I can send you a few of our publications. So we have done some work in this area. I can send it to you. Okay, any questions?
Sir, can you hear me?
Yes, yes.
Sir, one more keyword is there in the literature. What is predefined time stability, which is also tightly associated with the sliding mode control and its variants. So, if
Okay.
time permits and if it is convenient to you, sir, then please also give some lights on this predefined time control stability.
Okay, thank you. Yes, the predefined
Yeah.
time stability. So it means that so you are so sometime as I told you that the predefined. So the main concern is about the finite time. It means that you try to define it. But this definition is different from the fixed sign. The fixed sign, the time should be exactly the objective. But in the defined time, so it means that you are gradually reaching to the final time. That is exactly what I presented here. So for the predefined stability, so it means that you need to satisfy some bounded for the reaching time, and therefore you can basically do this exactly using the sliding mode control. So this is predefined. So basically, these are some keyboard basically for the addressing these two topics, the finite time or the fixed time. So the point is that in the predefined, if your objective is a fixed time, so the traditional sliding mode control only can guarantee the finite time, and then you need to see how to satisfy the exact time. So, but exact time. So, if you look at again the same formulation I showed you before, because we have this formulation v dot x, so it was less than the minus the gamma root of Vx. So all the discussion comes from here. Okay, so this formulation is for stability. And therefore, so this stability is for the given time. If the time belongs to, for example, the one the zeros are up to the t mean, so it means that if your target is the final time, so then you can do the SMC. Okay, then this is okay. But if your target is a fixed time for the given time or the predefined, so a stability time, a stabilization time, then you need to see how to make it, because this condition you need to reach to the equality, because you need to satisfy it for exactly the same function. But I can tell you that predefined or the fixed time, so it can be also possible by doing some modification of the Lyapunov function, because this Lyapunov function dx, because this Lyapunov function dx, this only can give you basically the finite time. But if you want to reach to the fixed time or the predefined, so we need to modify the Lyapunov function such a way that we can reach to the exact time. So what is the problem? The problem is that if your fixed time is become less than TR mean, for example, if your fixed time, so if the fixed time, so if the fixed time is less than the TR mean, so this is a problem. So this is a problem because you cannot go below of this value. Because if you go below of this value, then you have a saturation problem. So basically, for the control signal UT. And therefore, if you want to avoid this condition, if you want to avoid this problem, so you need to come back to your VX. So you need to come back to your VX and try to modify it. So now there are some publication. I remember that one of my PhD students, so she also published a few papers about this predefined and the fixed time. So I can send you this publication. But in fact, the main task is to do some modification the real-time function in order that we could satisfy to solve this problem. So as I told you, this is a very good formulation. So this formulation is very interesting, you see. So you cannot increase gamma too much, because if you increase gamma too much, then you can get the problem from the basically the control effort or the saturation. I think if you are interested, maybe I can share with you some publication, but we can discuss it because there are some issues maybe to be discussed individually, because these are more or less the topic is the same, but in fact there are some difference in the selection of the real function. Okay, so let's to show you some result about a sliding mode control and for some complexity. So I told you about NCS. I think you know about NCS. We discussed it before about the network control advantage, and we discussed about the CPS, and we also looked at this challenge about state awareness, data circulation, real-time analysis, and also the scientific decision, and also precise execution. So we discuss also about the communication control. But when it comes to the basic data, to the CPS and also network control, so we know that there are three parts. One is the plant, network, and also control. But also I show you we discussed about these three problems in the last lecture. But what I want to tell you today, so I want to tell you some complexity in the plant, because the first thing in the CPS or the NCS, so the first part is a plant. You see, the plant is the number one. The plant, it means that how to model it. So sometimes the dynamics are a bit complex. And that's it in my research, because I did a lot of research on this kind of the system as a Markov jump system, or the MJS, or the semi-Markov jump system, SMJS. So usually there are many CPS systems, so many CPS, so that they can basically can be modeled as a Markov jump or the Markov chain. The status of the system is changing. So the physical system may suffer from the abrupt structural change. Okay. So for instance, in the sudden environment disturbance or unexpected change of the operating point, or the parameter shifting. So for example, in the circuit, if there is such a switching, you see, between 1 and 2. So this switching, it means that you are jumping. So there is a jump, okay? So there is a jump from one to 2, or the vice versa. So this kind of the jumping from 1 to 2, and also from 2 to 1, or maybe the system remains at the same status. But this is a probability, you see, this is a probability. So now there is the topic we have in control. So we have the topic of a Markovian jump system. So the Markovian jump system is a stochastic process, but we are dealing with some probability. So the transition from 1 to 2 with the probability of the 0.7 we call it is a transition. We call it as a transition probability. Okay, the transition probability. Okay, so we call it the TP. Okay, so for the TP 0.7, the system goes from 1 to 2, or with the probability 0.3, it remains at 1. So now you can see that 0.3 plus 0.7, so it's equal 1. And this is also the okay from mathematics. So for the system number 2, it goes with the TP. Is a TP the 0.6 remains at the same system, but with the 0.4 goes to here, again the summation becomes 1. But I can tell you something about Markov jump. Markov jump has been developed a lot in the past. So I did a lot of research maybe 10 years ago or even more. 15 years ago, I did a lot of research on Markov jump. And currently, my students are doing also a lot of research on Markov jump. But I can tell you that the Markov jump has developed a lot. But one problem, the problem is this. So these are the some problem because these are the information, right? The 0.3, 0.7, 0.4, 0.6, these are the information. But in total information, it doesn't exist. We don't have. So if we don't have this kind of information, if we don't have this information, so what should we do? And that's it. So there is a lot of research on the uncertain TP or the unknown TP. So I want to tell you that the context of the Markov jump, the Markov jump system, has been developed a lot. For the full given information, it means that your information for TP is given, or is the partly uncertain, or the partly unknown, or even the full unknown. So I want to tell you that for all of these cases, so you are able to do some research and try to basically model your CPS, and then try to basically apply different control strategy. So if you are interested about this, so you can contact me, because this, as I told you, that this is one of our research areas. So let's back to the problem. The problem is that for the system description, so x dot is ax plus bu, and this is your initial conditions. But you can see that the matrix A depends to RT. Okay, the matrix B depends to RT. So it means that this system is the Markov jump system, and X is a state vector, A and B are the system S matrix, and the UT is the control signal. Okay, so this is the important part. So the RT for the T positive is a continuous time and discrete time Markov process. So now you see as the classic process. It means that the RT gives you some stochastic process, a Markov process. So what does it mean? It means that this RT, this set, it gives you some fixed value. It is so it takes the RT, it takes the values from the fixed this set from S is equal 1 to up to S. So what does it mean here? You have an S jump, okay? So the number of jump, or you have the S system. So because of the S, it means that you have this number of the system is switching between the S system, and then your RT, it takes one parameter from here. So now the RT, so this set basically belongs basically to S, okay? So in this case, so as I told you that the meaning of the RT is the transition from the current state, this is state I, to a state J. So the probability of transition to the after the time H, the transition to RT plus H equal J for the given RT equal R. It means that what is the probability goes from a state I to a state J, okay? So this probability is represented by this formulation. So this is equal pi ij. It means that this probability is a pi ij, and this is the definition in the Markov chain. So if the I is not equal j, so the pi ij h is a transition probability, and if it remains at I equal j, is a pi ir. So, and what is the h? So the counter h is also one offset we have for the we call it as like a sampling time. So it means that this parameter h, you can control the timing between the switching from one state to another state. So, but this parameter h also could represent also the topic of this Markov chain. So that's it. So this is also very interesting. So the parameter h is become more important in the SMJS in the semi Markov processing. Okay, so the pi ij is the transition rate. So at from I to t, point t to the node j. Okay, so now if you want to make the h is too small, because h is the time, right? So like a sampling time, and it's become more important in the context of the semi-Markov chain because in the semi-Markov chain, your transition are the function of h. So if the pi ij depends on the h, you have a semi-Markov process. But if it only pij, it becomes, for example, pij, so independent of h, then you have a topic of the Markov process. So now there is also one condition that, as I told you, that this condition for the probability so should be satisfied, and this is basically some condition we have on the transition rate or transition probability. Okay, so we have proved some theorems for stability. So for this system number one, so the system is stable if there exists some matrices like Pi, so such that this condition can be satisfied. So this condition is the stability condition. So Pi I transpose Pi plus summation of the J1 to S, Pi Js. So what is the problem here? The problem is H. Because the H is the one parameter for the Markov process, but how to satisfy this condition is one challenge. So a stability of the subsystem, for example, the subsystem from I from 1 to S, because I is from 1 to up to the S, so has no relationship with the stability of the whole systems. So now you see that the PIJH plays a key role in the performance. Okay, so the PIJH is very important. So basically for the stability and also the performance of the whole system. So just for your information that I told you before that this matrix pi, so this metric is a metric for the Markov chain process. These are the information. So I told you before that these are your information. If all is given, is a full information. Maybe some parameters are unknown, you see. So this means that you have some unknown terms. So now you can see that one challenge is propose the feasible stability condition when the transition rate are uncertain or unknown. Okay, so that's it. So we can say that one set could be all the transition, so should be given, should be known, or maybe some parameters for some index. So PRJ is unknown. So that's it for the matrix transition rate. So full information, some unknown terms. So that's it, or even some uncertain terms. In total, there are some classification. Some classification for these subsystems. It says that maybe some sets basically are is empty or not empty. So, but we have such a classification for the noun and for the unknown, and therefore we can make such a representation. Okay, but I'm not going to detail of Markov jump, but this is just for that information that in the cyber physical system. So if you want to make it a more accurate or more advanced modeling, so sometimes you need to add some probability based modeling. So then you can come to the Markov jump. So when you come to the Markov jump, the first thing is this matrix. So you need to look at what information you have. If you have all information, it's easy. But if you have something like this or some uncertain term, the task is difficult because you need to pay attention how to make it such a representation. Okay, but I want to tell you something about a sliding mode SMC for this, and that's it. I'm going a bit faster. But if you are interested, if you are interested to this particular case, you can basically look at these publications. So because we have done some research about stability. So for these different cases of the Markov jump, but this is just for your information. You see that for different case, so you can also think about some condition for stability. These are some condition for stability. Of course, you can find from these reference. Okay, so the one thing I want to also tell you about the network control for the context of CPS. So we talk about the time delay as a network constraint. We talk about the packet loss, packet disorder. So it means that if there is some network traffic congestion or there we have a packet transmission failures, network delay. So there we need to see that the delay, it can give some disadvantage for the poor performance or even instability. And the packet loss also can give you some consecutive packet loss. So it could be some disconnection of the networks. So in this case, this is about the problem we have. So in the context of the NCS. So the problem we want to solve it, we want to add consider the delay compensation. So if you look at this publication, so we have said that we can represent the lower bound, upper bound, basically for the transmission of the delay in the networks. Okay, so the delay, so the parameter of the delay, like the tau t, so it's a between the tau t is between the dm and also the dm, the capital dm, and also we add also one parameter t. So the parameter t is a partitioning time. So what does it mean? It means that for the time interval from tk to another sampling time tk plus 1, so we try to divide it to the some sub-interval, so based on the parameter t. So now you can see that for this interval I1 is tk to tk plus 3. I2 is from this sampling time to this time. So in this case, you can divide it to the several subsystems. And then this is a very interesting part as a time delay modeling for each subsystem. For this interval, the time delay can be defined like this: is a t minus IKT. For this part, the delay can be defined like this, and for this part, the delay can be like this. So this is basically we have it the modeling. So how to obtain the model of the time delay for the network system, and that's it. But for all of these delays, so they can satisfy this condition is always bounded, and also the derivative is 1. Okay, so if you need, you can find more details so basically in this publication. So now we come back to the network improve efficiency. So the first thing is that we need to look at the time triggering control. So because you remember that if you look at this kind of the TT, because this TT strategy as a time triggering strategy, is a very simple case to send the data over the networks. So, but in the time triggering control, the control task they can be executed in the periodic way. So now you have some periodical sending the data over the networks. But the TT has a problem. The problem for TT control is the wasting the computation and also energy resource of the battery. So the time triggering control is not a very popular approach because it has a higher computation time and also about the energy because the system should be executed in the periodical form. And that's it. You can open, of course, you can occupy the bandwidth, and that's it. You cannot reach the optimal usage of the bandwidth, and that's it. You could expect some congestion in the network traffic. So therefore, in the context of the network control, for example, here and also here, so you need to decide because if you have the data XT and here you have a sampling time XKH. So how to send the data over the network? Of course, the one issue is a delay, okay? So one issue is a delay, but there are many protocols to send the data. One is a TT, but we have also some other approaches we can discuss. So another approach is the event triggering control. For example, we can send the data over the networks. So if you want to use the event triggering control, of course, we have also some other lecture to discuss about event triggering control, but for your information, so event triggering control is a one approach you can execute the control depending on the predefined event triggering conditions. So in the event triggering control, you have some conditions where these conditions basically should be satisfied. So here you have a parameter, the omega, the parameter rho, and it means that for different sampling time, so these conditions should be satisfied. Okay, so here you can see the error signal. Error signal is a difference between the state at this sampling time, so minus the previous sampling time, xtkh. Okay, I will discuss about the event-based control also in the future presentation, but for your information that in the event triggering control or in the ET, so in the ET control, you should know one thing, the next releasing time. So this is very important, how to obtain the TK plus H. So because if you could obtain the next sampling time, then you can say that you know when the next data should be sent to the networks. So usually there are some mathematical issues to calculate the TK plus 1H. So based on the current time instant and based on some function. And this function basically so it depends on your predefined ET condition. So if this event triggering condition is satisfied for this minimum value of this time index, so basically if this condition is satisfied, so this would be your next sampling time. Okay, so I will also tell you more about this case because usually you need to remember that we have three topics. One is a TT, is the time triggering interval. We have an ET, is the event triggering interval, and also we have also the ST. The ST is a self triggering control. Self triggering control. So also I will discuss it in the next lecture. So about the self triggering control. So it's very important. So now you should know that why this when you need to choose TT and why you choose ET or why you choose ST. So these are the three different strategies So you can send the data over the networks. So for the event triggering control, the strategy is this. You need to first to obtain one conditions, and then you should obtain what is the next sampling time, the next time instant that you send the data. Okay, so now the for your information, so in my group, we have done a lot of research on the ET. So you should know that the simple way is to use a static event triggering mechanism, or even you can move to the dynamic event triggering mechanism. So what is the difference? So the difference here is that here I told you that there are two parameters as a design parameter. One is the omega, the second is the rho. But if the rho is constant, the rho is a constant, so then you have a static. But if the rho depends on the time, is a rho t, then you can think about some adaptation. And even basically, you can come to the use some intelligent approach. So you can combine it with the neural networks. But anyway, so you can contain basically this kind of the treatment condition. But you need to remember very important things. Important thing is the avoidance of the zero phenomena. It means that this phenomena so should be avoided because at the zero phenomena, so there is no data to be sent, and therefore, but even you should not send the two data to should have it one with the overlap in such a way that the system cannot react to the how the system have the control signal and react to the reach sampling time. So the zero behavior, so basically should be avoided. And in this case, there are some basically the research, but I can explain you in another presentation about the triggering mechanism, xeno behavior, how to avoid, how to. These are something we can discuss it later. Okay, so when it comes to the distributed system, so okay, I think we can have a break now. I think it might be fine. So if you agree, we can have a 10 minutes break. Is it okay? Okay, so we can start after 10 minutes, okay?
Okay, sir. 10 मिनट का break हो गया.
Okay, so let's have a 10 minutes break and please come back in 10 minutes. 10 minutes.
Okay, sir.
get a better decision after observing the information. And that's it. The symptom is very important, but the symptom in the AI means the feature, okay? So if you come to these topics, then you need to look at the features, and the features gives you different basic symptom. And that's if you are using the deep learning